everyone! Welcome to today's lecture on the molarity of leftover ions. Now you may be thinking to yourself, hey, we've already learned how to calculate the molarity of leftover ions. We did that in Chem 1. And you're right, we did do that in Chem 1. But we used stoichiometry to calculate the molarity of leftover ions. Today we're going to learn how to calculate the molarity of leftover ions via ice tables. So we're going to learn a new type of calculation today, this ice table thing. So we're going to learn about it via the molarity of leftover ions and stoichiometry because you're already familiar with these topics. We're going to use these ice tables though when we start looking at equilibrium and acid-base reactions and titrations and things like that. So we need to get familiar with these ice tables and then we can use them in the rest of the course. So let's start off and pretend we're making a cake, and this is a chemistry cake. And you have in your kitchen 20 cups of flour, 8 cups of sugar, 15 gallons of milk, and 48 eggs. You have a really big kitchen and you just decided to fill it up with lots of random ingredients. And so the recipe for our chemistry cake is going to be 3 cups of flour, 2 cups of sugar, a half gallon of milk, and 6 eggs. And this will make our chemistry cake. I actually don't know if this makes a cake or not. I just kind of made some numbers. So don't actually go and try and bake this cake, or do and, tell me how it works out. So this would be our cake. So I want to know, with the ingredients in our kitchen, how many cakes can I make? And which ingredient runs out first, and limited the number of cakes you could make. That would be our limiting reagent, right? And then how much of each ingredient is left over? And really, what does this assignment have anything to do with chemistry, right? So let's go ahead and check this out. So here is our equation, if you will, our recipe, and I wrote it as equation. So we have 3 cups of flour, plus 2 cups of sugar, plus a half cup of milk, plus 6 eggs, and that's going to make our chemistry cake. So we are learning about ice tables today, right? And so this is down the left side. So I stands for initial. So I'm going to write how much of each thing we start with. Okay, so we had in our kitchen 20 cups of flour, 8 cups of sugar, 15 gallons of milk, and 48 eggs, okay? Oh, sorry, I think I said this was a half cup of milk. It's a half gallon of milk, my apologies. Regardless, so that's what we are starting with. And we put a 0 here because we don't have any cake to start with. And that's going to be true for most of our reactions. Our products are going to be 0 because we're not starting with any, right? We're just dumping in reactants. So then we need to figure out, okay, well, we need to figure out how many cakes we can make with our given ingredients. And so normally what we would do is we would, do dimensional analysis for each one of these and figure out how many cakes each one could make, right? And then we can go back, and figure out which one's limiting and all of that kind of stuff. This one I'm going to do just kind of by inspection, which means I'm just essentially going to look at it and kind of talk through it. But I'm going to show you how to do this not using stoichiometry. So if you were in my class before, we like to make train tracks, right? Dimensional analysis. We're not going to do that. So right now I'm just going to kind of look at all of these. So if we think about this 20 cups of flour, right? That we're going to make, just under 7 cakes, because if each cake takes 3 cups of flour, right, we'd make 6 2/3 cakes. So I'm going to say that this is about 7 cakes we can make. And then if we look, we need 2 cups of sugar for each cake, and we have 8 cups of sugar, so we could make 4 cakes. And for the milk, right, we have 15 gallons of milk, and in each one, we need a half gallon of milk, so we could make 7.5 cakes. And, we have 48 eggs. We need 6 eggs in each cake, so we can make 8 cakes. Okay, so in looking at each one of those, it looks like our sugar is going to limit us, right? We can only make 4 cakes because we only have 8 cups of sugar, right? And we need 2 cups in each cake. So that's going to be what we're going to use. And so all of these here, these will get a negative. So we're going to use up 8 cups of sugar, and we're going to make 4 cakes. Okay, so that will get a plus sign. All of our reactants will get minuses because we're going to use them up, and all of our products will get pluses because we're going to make them. This is our change row. Okay, so this is what's happening. We are using up 8 cups of sugar to make 4 cakes. So then I go through and I'm going to figure out, okay, well, how much of each other thing did I need? right? Our sugar is going to run out. It's going to be our limiting reagent. So we're going to multiply everything by 4 because we need 4 cakes. So, right, so we started with 3 cups of flour. So our change would be 12. We're going to use up 12 cups of flour. And then we're going to use up 2 cups of milk because 2 gallons of milk because 1/2 times 4 gives us 2. And then we're going to use up 24 eggs because 6 times 4 gives us 24. Okay, so that's our change. And then our last row is our end, or it's sometimes going to be our equilibrium. But for now, since this reaction, goes to completion, right? We're not going to have an equilibrium between our cakes and our eggs and things like that, right? We won't get our ingredients back at some point if we leave our cake on our counter. So this is going to be end rather than equilibrium. But we are going to go through and add together. So 20 plus a negative 12, right? We're just essentially going, this line plus this line. 20 plus negative 12 gives us 8. 8, plus a negative 8 gives us 0. 15 plus a negative 2 gives us 13. 48 plus a negative 24 gives us 24. And then 0 plus 4 gives us 4. So this is how we do ice tables. We start off, right? In our first line, we're going to write how much we start with. In the second line, we're going to spend the most time working on the second line. That'll be our change line. And then the end line, you're going to take your first 2 rows and just add them together to get the end. Okay, so our sugar was our limiting ingredient. All of the other ones are in excess, and we were able to find out how much we had left of everything. And we were also able to figure out how many cakes we made. So like I said, we already learned how to solve the molarity of leftover ions problems. And like I was saying before, we used these 2 sets of dimensional analysis or train tracks to determine the limiting reagent. But as you can see, it's really easy using these ice tables because it will literally say 0. That one's limiting. It ran out, right? It's really easy to see. And so these are really helpful. So we used this to figure out, the amount of product that could be formed from our limiting reagents, the amount of ions that were left in solution, all kinds of good stuff. But like I said, in this class, we're going to learn how to solve these problems via ice tables. So when you're working on that worksheet, do not use the methods that we learned in Chem 1. We're going to use ice tables to get practiced with ice tables. If you're not understanding how to use them still after this whole lecture, please let me know or go to SI, right? So you can figure out how to solve these problems and you can get help because we are going to use them for the rest of the course. So it isn't like, I didn't understand this one assignment. It'll be okay. It won't be okay. You need to figure out how to do it. So typically, when we're doing this whole train track method, it's really algorithmic, right? We start with grams, we change our grams to moles, right, using the molar mass. Then we use our mole ratio from the balanced chemical equation to find moles of something else. And then we use the molar mass of that thing to figure out how many grams it is, right? And we do this whole, train track, unit canceling, dimensional analysis, right? But it doesn't really require you to understand very much. As long as you can plug the numbers in and you know how to cancel out units, then it kind of works out for you. That's not going to be how it's going to play out in this class. You need to have a better conceptual understanding of the types of problems that we're solving. So ice tables are actually going to work out better for you. It's not necessarily easier. And I think at the beginning you're going to think, why am I doing it this way? It's harder or it's different. It's a lot of things, but it's a better conceptual understanding, which is what we're trying to go for about these stoichiometry calculations. And it's going to really clearly show the limiting and excess reactants, which is really, really nice. But the most important thing here is that it's going to prepare you for the equilibrium calculations that we're doing very soon. Okay. So what are ice tables? Ice tables are going to be composed of the number of moles, right? In this stuff that we're doing right now, this molarity of leftover ions and stoichiometry, we're going to use the number of moles. When we get into equilibriums, a lot of times we'll use the concentrations as moles, but this is just because the volume isn't changing. In the problems that we're doing right now, sometimes the volume changes, sometimes it doesn't, and it actually is going to simplify your life if you just use the number of moles. But you may see it in later chapters using the concentration of molecules, but again, it's because the volume isn't changing there. That's why we can do that. But we're looking at the number of moles in different stages of the reaction, right? In the beginning and at the end, or at equilibrium, right? That E value. The ice tables automatically set up and organize all of your variables and constants, which is really nice. It's a really easy way to kind of set things up, and it's easy to keep track of everything. So I, again, stands for initial. That's going to be how much you start with. So right now it's going to be the initial number of moles. Sometimes it'll be your initial concentration, right? But it's always the initial. C is for change. And like I said, we're going to spend the most time talking about the change. You're going to write it either as positive or negative signs, and then a variable, like we might write minus 2x or plus 3x, and because we're writing an increase or decrease from the initial value. And then E is for the end. Sometimes, like I said, it'll be equilibrium. It just depends on what chapter we're looking at, or whether your reaction has a forward arrow or is, a double-headed arrow like that. If it's a forward arrow, then it would represent end. If it's a double-headed arrow, then it's equilibrium. But either way, this is the summation of the initial and change rows. So you're going to add up the first two rows. Here's our procedure. So if you want, you can print out this slide. This is going to tell you how to do it. I'm going to walk through this whole thing twice to show you how to do these types of problems, okay? The first thing you'll do, make sure you have a balanced equation, set up your ice table. And then you're going to fill in your ice table with the initial mole amounts of everything. And then you're going to figure out how many moles it requires to use up each one of the reactants, and you're going to figure out the smallest value for X. We're going to, spend a lot of time doing this. Then you're going to fill in your change line of the ice table, and then you're going to, fill in the E line by adding them together, and then use the E line to figure out anything else you might need, maybe the mass of the product or the the amount of the excess reactant or whatever the case may be. But this third line, that's the trickiest one. Anyway, let's go ahead and try this out. I think you'll find it's easier once we get going. So here's an example problem. 14 moles of gallium and 12 moles of oxygen gas react to form gallium oxide. Determine the limiting reactant, the mass of the excess reactant, and the mass of gallium oxide produced. All right, first thing we need to do, make sure you have a balanced equation and set up the ice table. So here's our equation. Gallium plus oxygen gas gives us gallium oxide. I'm going to stop you just for a second to remind you that there are 7 diatomic elements. I like to remember them as Hofbrinkel. Okay, so hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. Anytime those elements are by themselves, like oxygen is here in this equation, make sure they get a 2 after them. They are diatomic. Whereas you see gallium does not show up in Hofbrinkel, so it doesn't have a 2 after it. And then obviously we got this by doing, gallium is a 3+, oxygen's a 2-, and then we make our formula. Okay, in this class, I'm going to assume that you know how to write reactions, because you should know how to write reactions. And I'm going to also assume that you know how to balance the reactions. So we go through and, we need to make our oxygens equal. They both go to 6, which means that we need a 4 in front of gallium. Okay, so that's the first bit, and then set up the ice table, ICE. Okay, our second step is to begin filling in the ice table by writing in the initial mole amounts of each species. All right, so we have 14 moles of gallium and 12 moles of oxygen. So we'll go ahead, 14 moles of gallium, 12 moles of oxygen, and then we don't have any gallium oxide because, we only have our reactants. So those are the first 2 steps. Pretty straightforward. Make your balanced equation, write ice down the left side, and then fill in the I line. All right, next bit. Number 3, determine how many moles it will require to use up each of the reactants and choose the smallest value to use for X. Okay, so this, we're going to assume that each one is going to be the limiting reactant. And normally we would do this kind of via stoichiometry, right? You would do a mole ratio and figure out maybe how many moles of gallium oxide you could make, and then whichever one was the smallest, right? That whole process. We're going to do it a different way, okay? So just kind of put that out of your mind. Different way. So we're going to assume, before we get to that, we're going to assume that we don't know how much each thing is. right? But we are going to use these coefficients in the front, and we're going to use the value of x. And this x is going to represent the mole amount. Okay, so because there's a 4 in the front, it's 4 mole equivalents will get used up. Okay, so we will put a minus 4x. And then for here, we put a minus 3x. Again, both of these are getting minus or negative because they are going to be used up. And then we're just using their coefficients to put here in front of x. And then on the product side, we're putting a positive sign because it's our, we're making that, we're forming that in the reaction. And again, we're carrying that coefficient down. Okay, now we're going to go and figure out, okay, what might x be? So to determine the limiting reagent, we're going to assume that our E line is 0 for each one, which means that 14.0 plus a negative 4x equals 0. So that's what I have here. 14.0 minus 4x equals 0. So that's just adding this down, assuming our equilibrium line is 0. Okay, so then we will go ahead and rearrange that to solve for x. So we, move the 4x, we add 4x to both sides, we divide both sides by 4, and we get x is 3.50. Then we're going to do the exact same thing with oxygen. We're going to say, okay, 12 minus 3x gets us 0. So that's this one. 12 minus 3x gets us 0, and then we'll go ahead and solve for then what would x be? X would be 4. All right, now in looking at these, we were going to pick the one that is smaller. So that still stays the same with the limiting reagent stuff. Okay, the smaller one is at 3.50, so that means that our gallium is limiting. Okay, so now that we know our values of x, instead of having our x's in our ice table here, we're going to go ahead and fill in this 3.50 for all of those values of x. So this will be negative 4 times 3.50, and then negative 3 times 3.50, and then 2 times 3.5. Sorry, this should be 3.50 for sig figs. But all I did from there to there is I filled in those values of x. Okay, when you are doing this, on your paper, you can do this however you like. You see I removed all the x's and I filled them in with the values. That's because I normally do this step before I fill in my C line. So I actually don't write, that all with x's for stoichiometry. I go and I solve for what x would be first, and then I fill in my C line. And then lastly, we are going to solve for our E line, which means we're going to take I plus C to give us E. So 14.0 minus 4 times 3.50 gives us 0, which is good because we determined gallium, right, was our limiting reagent, so that should be 0. And then we're going to do our oxygen. So again, we're going to add these two lines up. So 12 minus 3 times 3.50 gives us 1.5, and then 0 plus 2 times 3.50 for both of these, my apologies, gives us 7.0. Okay, and this would actually be then 7.00. All right, so now these are our numbers of moles of everything at the end of this reaction. Okay, so we have no gallium. That was our limiting reagent. It's been used up. Oxygen would be our excess reagent, and we have, our product, our gallium oxide. So again, gallium is the limiting reagent because there are 0 moles of gallium left after the reaction. All right, let's deal with this other stuff. Determine the mass of the excess reactant. So we want to figure out the mass of our oxygen. We know that we have 1.5 moles of oxygen, but how many moles is that, right? So then you can make a quick little train track or however you'd like to do this, right? And we figure out, okay, for every 1 mole of oxygen, that's 32 grams. We make sure our units cancel. That gets us 48 grams of oxygen that are left over. All I did was I converted my 1.5 moles of oxygen into grams. And then we can figure out the mass of gallium oxide produced. So again, we're going to take our moles of gallium oxide and we're going to turn that into grams. So we take our moles of gallium oxide, we use our molar mass, and we're going to convert that into grams of gallium oxide. Okay, and we get there are 1,300 grams of gallium oxide produced. So that's it. That's how we do this. So I know it might seem a little cumbersome, and you might think that, okay, doing this via stoichiometry would be faster and easier maybe because you understand it. But again, I want you to do these types of problems as ice tables for now so that we get really good at understanding how to do them. Okay, here's a practice problem. I want you to go ahead and pause here and try this one. Okay, this is really, really, really similar to the last one we did. And like I said, I would go back to that slide that kind of told you all the steps and use that while you're getting good at solving these problems. And then, obviously once you get better at them, you can take away that crutch and solve them on your own. The only thing that's different here is that instead of starting with moles, I've given you grams of your reactants. Okay, so before you can even put this stuff into an ice table, you need to convert your grams into moles because only moles can go in your ice table. You cannot do ice tables in grams. Like I said, later we can do it in molarity sometimes, but for now you're only allowed to do ice tables in moles. So you're going to need to convert your grams of aluminum into moles of aluminum and your grams of chlorine gas into moles of chlorine gas before you can even start the problem. Once you're done, come back and I will show you the solution. All right, here we go. So 14 grams of aluminum reacts with 48 grams of chlorine gas to produce aluminum chloride. Determine the limiting reactant and calculate the masses of the excess reactant and product that are left after the reaction. So our first step, check to make sure you have a balanced equation and set up your ice table. So we have aluminum reacting with chlorine. Again, remember chlorine is diatomic because it shows up in Hofbrinkel, and it produces aluminum chloride. We'll go ahead and we'll balance it and we'll be good to go. Set up our ice table, on to the next step. All right, begin filling in the ice table by writing in the initial mole amount of each species. So again, like I was saying, you don't have moles right now, you have grams. So our first step needs to be to convert our grams into moles. So we have 14 grams of aluminum, and we'll take that, we'll make a quick train track, and we'll convert our 14 grams of aluminum using the molar mass into moles of aluminum. So that gets us 0.519 moles of aluminum. So that goes there. Then we'll do the exact same thing with our chlorine, and we'll take our 48 grams of chlorine, we'll use our molar mass of chlorine, and we will convert that into moles of chlorine. And we will put that in for our initial amount of chlorine. And then, like I said before, we don't have any aluminum chloride because that's our product, so that will be a 0. All right, step 1 and 2, done. On to the next one. So step 3, right, is to figure out that x value. So all of these, this would be minus 2x, minus 3x, plus 2x. And again, we're taking, the minuses are because those are reactants, so they will be being used up. The plus is because that's a product, so it will be being produced. And then all of these are just the coefficients from the balanced chemical equation. Then we can go through and actually figure out, okay, what are our values of x? So for our first one, right, remember, we're always going to assume that this is going to be 0. So it's going to be 0.519 plus a negative 2x gets us 0. And then we'll solve for x, and that will get us x equals 0.260. And then we'll do the exact same thing for chlorine. We're going to say 0.677 minus 3x gets us 0. And we'll solve for that x. And again, we're always looking for the one that gives us the smaller x. So since chlorine gives us the smaller value for x, that is the limiting reagent. So that means that all of the chlorine will get used up in the reaction. So then we can go through and we can plug in 0.226 for all of those x's. So now we have, negative 2 times 0.226 and so on and so forth, right? We just plugged in that value for the x's. So now we'll go through and we will, do our E value. So that is I plus C gives us E. So 0.519 minus 2 times 0.226, and we'll, calculate that, and so on and so forth. Remember, chlorine should be 0, right? We based our calculation on chlorine because it is our limiting reagent. So if it doesn't come out to 0, you've done something terribly, terribly wrong. All right, so now we can use our information from our E line to, actually answer the question. So chlorine is our limiting reagent because there are 0 moles of chlorine left after the reaction. And then we're going to figure out the mass of our excess reactant. So that would be our aluminum. We'll take our moles of aluminum, right, and we'll use the molar mass of aluminum to convert our moles of aluminum into our grams of aluminum. And that will be our mass of aluminum that's left over after the reaction. And then we can do the exact same thing to figure out how much product is left after the reaction. So we're looking for aluminum chloride. So we'll take our 0.452 moles of aluminum chloride, we'll use the molar mass of aluminum chloride and convert that into grams. And there you have it. That's how you do these types of problems. Hopefully, once you did it by yourself, you see that it's not quite so bad, and you will get faster at these. And actually, you'll end up finding that these ice tables are oftentimes faster than doing all of the stoichiometry because you can, find out a lot of information from this E line. Once you get to this E line, right, we can do a lot of different, mathematical calculations with that because we know how much of everything is left after the reaction, which is really helpful. But that's it for today's lesson. You have a worksheet that corresponds to this lecture. The worksheet starts off by doing another practice problem. So if it still wasn't clear after this lecture, make sure to read through that really, really carefully. When you're working through that, the worksheet, you're also going to review a little bit about molarity. Okay, and you're going to use molarity to find moles. Like in this practice problem, this last one, we used grams at the beginning to find moles before we did our ice table. Okay, well in this worksheet, you will use, the molarity and a volume to find moles before you do these practice problems. Okay, you should know how to do this. This is solution stoichiometry. We covered this a lot in Chem 1. But yeah, so just make sure you are always doing your ice tables in moles. That is the key. Like I said, though, get lots of practice doing these types of calculations. We are going to use ice tables for the remainder of the course, pretty much. We're going to use it in almost every chapter. So make sure you understand how to use them. And if you don't, ask questions so you can get some help. As always, I will see you all next time.